All right, APL class, we are going to do the last section for this unit that we're working with integration. And in this section, we are looking at U substitution. So there's going to be certain functions that we look at where you can't, just straightforward use the power rule because integration doesn't necessarily have a chain rule or product quotient rule. Sometimes we have to change the way that our function looks a little bit by making what's called a U substitution. Okay, so we're going to take a look at U substitutions with e to the u, change of variable method, I think that'll be in the next video, substitution with some definite integration, and then antiderivatives of e to the x and then a to the x. Okay, so sometimes it's easier to just jump into the examples, but basically what we're doing is we're making a substitution. We might have a composite function that would involve a chain rule if we're doing the derivative, and what we're going to do is we're going to kind of rewrite our antiderivative so that we don't, so that this, this chain rule is done kind of on the side beforehand, and I'll show you what I mean. So here's kind of the idea. If you have a product of two things, that's, a typical giveaway. If it's not easy to simplify, like here we could expand this to the fourth power, but that's going to take a lot of tedious work. So what we want to do is recognize some things in here and say, well, this part of it is an x squared and this part of it's 2x. So this is how we do our U substitution. We want to write a simpler function, and the general rule is if you see part of it that if I were to take the derivative of it, it becomes the other part. That's the way you want to begin setting this up, and you want to let u equal the part that has typically the 1 degree higher than the other part, because when we take its derivative, which we're going to call du, that will turn into the other piece of that function. So if I let u equal x squared plus 1, then my derivative of u, in with respect to x, so it's du dx, the derivative of u with respect to x becomes now 2x. Now what I want to point out here is what I've got now. I've got x squared plus 1, and then I've got 2x. Okay, and those pieces, x squared plus 1 is right there, right? And then 2x, make this a little bit smaller, 2x is right there. So those are the two parts that I have and that I want to substitute for, and I'm going to rewrite this function so that it's all in terms of u and du. So when I say u and du, when I do my derivative of the u with respect to x, the other step is you're just going to solve for du, and by multiplying that dx to the other side, so I have 2x dx like this. So now when I rewrite this original, the 2x gets replaced with du, the 2x dx, and then the dx is also, I should highlight that because that's part of what we have originally. And we want our variable of integration to become u in this case, so we'll have a du in there. Okay, so when I rewrite this, let's see if we can follow this. So the x squared plus 1 is going to become the u. So now instead of x squared plus 1 to the fourth, I have u to the fourth. And then the 2x dx, right there, 2x dx is going to become du. So now I am able to rewrite a much simpler expression that involved, basically a derivative in there. Okay, and so now I've got just the antiderivative of u to the fourth du instead of all of this. So now I can integrate this, and there's no, products or anything in there, because as I did my derivative, it form fit into exactly what I have right here. So when I integrate this, I have u to the fifth over 5 now, u to the fifth over 5, or 1/5 u to the fifth, plus c. And now what I want to do at this point, that is my antiderivative of what I had in terms of u, but now I want to substitute back in for the u. The u is x squared plus 1. I want to put that back in there. So my final solution to this one would be x squared plus 1 to the fifth all over 5, or 1/5 times that, and then a plus c afterwards. Okay, so we're going to practice more. I know that maybe seems confusing seeing it for the first time, but I think when we do a couple more of these, you'll hopefully pick up on this pattern. Okay, so again, you want to write a simpler expression. So here I've got a product, and I've got like a square root in there, and so this would be really messy. There isn't, you really can't expand it because this is under a square root, so you couldn't even really do that. So a u substitution is necessary here. So again, let's let u equal the the part of this function that has the higher degree, which would be the u cubed plus 1. So when I do the du, the derivative of that, I'll get a 3x squared, and that's what I want to see happen there. Then everything will fit just like it did here. So I've got x cubed plus 1, and then when I do derivative of u with respect to x, and right away I'm going to move that dx to the other side. I get 3x squared, and then I'm going to put the dx there, right? So it would have been du over dx, but I'd multiply it over just like I did right here. Okay, and now look at the parts that I have. I'm going to highlight these again. So I've got the x cubed plus 1 right there. That's going to become a u, and the 3x squared dx right there, that's going to get substituted right there with du. So now it's just going to be the square root of u and du, and it becomes a much simpler function to integrate. Okay, so I've got square root of u du, and so the u, the square root of u, is representing the square root of x cubed plus 1, so I'm letting u equal that. The derivative of u, right, is going to be 3x squared dx, so I've got the 3x squared there and the dx, and that's just going to get replaced with the du. Okay, so now when I integrate this, so that's a u to the 1/2 power, right? So if I add 1 to 1/2, that's 3/2. If I divide by 3/2, that's 2/3. You're multiplying by 2/3, and so I got 2/3 u to the 3/2 plus c. Okay, and then I'm just going to substitute back in. My u was x cubed plus 1, so I got 2/3, and I've got x cubed plus 1 to the 3/2 power plus c. Okay, so let's take one more of these. Now this one obviously has some trig stuff in it, but again, what you're thinking is I want to let u equal the piece that when I take its derivative, it'll equal the other piece that's in there. And usually, like I said, there's usually a product of some kind that's in there. Okay, so I see here I've got tangent plus 3. But if I do the derivative of tangent, I know that that's secant squared. So I want to let u equal the tangent part of this, tangent x plus 3. That way when I take derivative of that, du dx, and move the dx over again, that's secant squared, and the 3 derivative of 3 is 0, so that disappears. And then it'd be du dx. I'm going to multiply that dx over to this side right away. Okay, so once again, I can replace, so tangent x plus 3 is going to be replaced with a u, and the secant squared dx right there and right there, that'll get replaced with du. So I have a pretty simple expression again. Now it's just going to be, again, this part just becomes u, so I'll have u, and the secant squared dx is du, so it's just really just u du. That's it, easy. So my variable is u, so that'd be u squared over 2 when I integrate it, plus c. And then I just plug back in terms of x, u is the tangent of x plus 3, so I'll have tangent of x plus 3 squared over 2 plus c. That's it. So those are some pretty straightforward recognizing patterns. Those ones worked out really nicely. Now they don't all work out quite as cleanly as those ones did, but sometimes there's a little adjusting that we need to do to make it fit the way it needs to. So that's what we're going to look at on these next examples, where we have to do just a little bit of a minor adjustment, okay? But you're still kind of looking to set it up, with that same basic idea in mind. So I want to let u equal the x squared plus 1, so that when I do the derivative, I get something that has x to the first. Now it's not exactly going to be 2x like we see, but this is where the minor adjustment comes in. Okay, so I'm going to let u equal x squared plus 1, which means du is going to equal 2x, and the dx, I'm going to multiply it over right away. Now, here's the issue. We don't have 2x dx, we just have x. Okay, and I want it to look exactly like what I'm given here. So in order to do that, what we can do is divide. We can divide by 2 in this, and I'd end up with 1/2 du would equal x dx. And it's okay if I have a constant of 1/2. That's pretty easy to work with, but now I've got the pieces that fit, that form fit perfectly, the x dx right there, right? And then I've got the x squared plus 1 that I let equal u. So I'll have, let's think about this. So the x squared plus 1 gets replaced with u, so I'll have u to the 5th in there, and then the x dx gets replaced with 1/2 du, right? And the 1/2 isn't a big deal. That can just get pulled right out in front of my integrand, right? So when I rewrite this, I have u to the 6th, right? U to the 6th, and then I have times 1/2 du, right? Now that 1/2, I'm just going to take that right out here right away, right? The 1/2 du, 1/2's a constant. You can just pull that out there, and then it's still pretty easy to work with, okay? And now I can integrate u to the 7th over 7, so I have 1/2 u to the 7th over 7, you know, and over 7, really, that's going to change this to like a 1/14 in front, since it's over 7, plus c, right? So I've got really u to the 7th over 14, u to the 7th over 14 plus c, and then I'm going to plug back in my x squared plus 1, so I got x squared plus 1 is what my u value was, to the 7th over 14 plus c. Okay? So there, our minor adjustment came in this step right here, because when I did my derivative of u, it was 2x. I just needed an x, so I end up having to divide by 2 or multiply by half, and then that ends up being like, a constant that you're going to put right in front of your integral sign. Okay. Next one, in this one we really only see one expression there. But because we're taking a square root of that, and it would be like 2 1/2 power, and we don't have a chain rule for integration, we want to let u equal the radicand that's under there. So u is going to equal 2x plus 1. And when I do the derivative, it's kind of like there's nothing else but a 1 multiplied there. When I do the derivative of this, I end up with 2. So when I do du, I get just 2, and my dx, again, I'm going to multiply that over. But I just have dx. I just have like 1 dx there. So again, let's divide, or divide by 2 or multiply by half. So 1/2 du is equal to dx. Now once again, let's form fit this. So I got the 2x plus 1. That's going to become a u that I highlight in green, and the dx that I have right here, that's going to become 1/2 du. So I've got square root of u, and then 1/2 du. The 1/2 can pull out, so I'll just have square root of u du. Okay, so I'm going to have the 1/2 again out here, and then I'll have square root of u du. And I know how to do a integral of a square root of u, or a square root of anything, and so it's 1/2 power, so I add 1 to that 1/2, which is 3/2, and divide by 3/2, which is 2/3. So I got a 1/2 here, and then I've got 2/3 u to the 3/2 plus c. Okay? And now I can simplify this a little bit, right? And so I get like 2/6, or that would be 1/3 u to the 3/2. And now that I've got it to that point, now I'm just going to replace my u with the 2x plus 1. I'm kind of running out of space. I'm going to go back up top here. So I've got 1/3 u, which now becomes 2x plus 1. And that is to the 3/2 power plus c. All right. So again, we're going to let u equal that, in this case the radicand, because when I do the derivative of that, it drops it down to a constant, and then that's all I have left is that dx, like a 1 dx. But so I had a 2 dx, I need to divide by the 2 or multiply by the half, so that I can have to have that 1/2 out in front. Okay. Now in any of these, as you're done with them, you can go back through and do the derivative and check to see that you get what you started with, right? And I don't have room to show that right here, but you could maybe do the first steps of it. 3/2, times your 1/3, that would be 3/6, which would be 1/2, and then times 2x plus 1 to the 1/2, but then times your chain rule is times 2. That's what's going to cancel out that 1/2 again, if you kind of think that through in your head a little bit. Okay, part C. So this one, we have a quotient. We've got like a square root inside of that. But, so we want to let u equal, again, the one that has the higher degree on the term, because when we do derivative, we want it to become something close to this other part, okay? So let's let u equal the 4x cubed minus 5, all right? Oops. So u equals 4x cubed minus 5. Derivative of that, du, is going to be 12x squared. And I'll put the dx after that again, like always. Okay. Now, that's not exactly what we have up here, right? We've got 7x squared, but the x squared is the important part. That's what we really need to be able to substitute for, right? Now, the 7 that's there, that really can just can get pulled out, and the 12, we'll have to get rid of, we'll divide by, just like here where we divided by 2, we had a 1/2 out there. We'll divide by 12, we'll have a 1/12 out there, but also we'll pull that 7 out, so we'll technically have like a 7/12 out in front of our integrand, okay? So 1/12 du is going to be my x squared dx piece, okay? So again, x squared dx, I've got that part covered, x squared dx. That's going to get replaced with a 1/12 du. The du I'll leave, in here, the 1/12 I'll pull out. This 7 here, I'm also going to pull that out because that's a constant, which is going to leave me 7/12, okay? And then the denominator, that's pretty easy to see that that's just going to change into u. I've got 4x cubed minus 5, which I called that u, okay? So when I set this one up, like I said, we're going to have 7/12 on the outside, okay, because of the 1/12 here, and then pulling the 7 out. 7 times 1/12 would be 7/12, okay? And then we'll have 1 over square root of u du, just like that, right? And so when I integrate that, right, so that's like u to the negative 1/2. I'm going to do some side work here and just going to talk about this, but this would be a good one to just kind of remember the pattern on how this works. But so if I have this expression, right, that's the same as u to the negative 1/2, and if I integrate that, I add 1 to that negative 1/2, which gives me positive 1/2, and then I'd be dividing by, so I'd be dividing by 1/2, it'd be like times by 2. So if I integrate this thing, right, so I'm going to have u to the 1/2 divided by 1/2, which would be like 2u to the 1/2, like that. Okay, so that would be what this expression changes into after I do the antiderivative, right? So it'd really just be 2 square root of u. So hopefully you can follow that. So I'm going to have 7/12 and then times 2 square. I'll just go back to a square root of u plus c. All right, and I'm going to erase this, and then I'm going to just substitute back in with the u being represented as 4x cubed minus 5. So that's 7. Well, you know what? When I multiply that, 7/12 times 2 is going to become 7/6 if I reduce that 14/12. So it's going to be 7/6, and then the square root of 4x cubed minus 5 and plus c. Oops. All right. So those are some, u substitutions where we had to do some minor adjustments, they would say. Okay. And those had to do with, like dividing this out, or pulling a constant out off that 7 and things like that. Okay. Okay. I think we can get through. Let's get through example 3 and, well, I think we can do 3 and 4, and then I'll finish up with the rest of this in another video. Okay. So it says, yeah, you'll have to do some of these with some trig functions as well. And so with example 3 part A. So we can integrate sine of x, and we know that the antiderivative of sine of x was negative cosine of x. If you remember that pattern, I remember I drew this for you before. Where you got cosine x and negative sine x, negative cosine, and positive sine up here. And when we go clockwise, we're doing derivatives, but if we go counterclockwise, then we're doing our antiderivatives, right? Antiderivatives this way, okay? But if if there's something there other than just x, then we have to think about this, the chain rule and using u substitution. So if I let u equal 2x, du is going to equal 2 dx, or 1/2 du would equal dx. So when I set this up again, so I'm going to replace the dx right here with a 1/2 du, and the 1/2 I'm going to pull that out here. Okay, 1/2 out there, and then I've got sine of u du, right? So the du was replacing the dx with the 1/2 that I pulled out there. Okay, so antiderivative of sine is negative cosine. So now I've got, the negative, I'm just gonna put it there, and I've got cosine of u plus c, and then the u I can substitute back for as 2x, and then that's it. Okay, so as far as what, the one thing that we had to worry about was the fact that there was a 2x there, and that caused me to need to put a 1/2 in front, and I like to demonstrate that with the u substitution here. Okay. All right. Next one, we've got a cosecant squared of theta. They're using theta now instead of x, and so it's theta over 4. Okay. And so if we let u equal again that theta over 4 in a similar way, the way they had a 2 here, if we let u equal theta over 4, and then du, and instead of dx it'd be like d theta, because that's our variable, that would just be 1/4. This is like x over 4, 1/4 x. When I do the derivative, it's just 1/4. But again, theta is my variable, so then I'd put the d theta right there. That's what we have, right, for variable of integration. Okay, and we du d theta, multiply the d theta over. All right, so in the end, this, I have a d theta, but I don't have a 1/4, so I'm going to multiply in this case by 4. So it's like I have a 4 du equals d theta. Okay, so d theta is going to get replaced with 4 du, and again that 4, I'll pull that out in front. So I'll have 4 times the integral of cosecant squared of now u, right, and then du. Right? So du, which was replacing d theta with a 4 multiplied there that I moved out. Now the antiderivative of cosecant squared, that was negative cotangent, because the derivative of cotangent was negative cosecant squared. Okay, so when I take the antiderivative there, it's going to be the negative. I'll put that in front of the 4, negative 4 cotangent u plus c, and so that would be negative 4 cotangent, and now we're going to change that back to our original variable theta, which was u is theta over 4 plus c, just like that. Okay, and the last one here, we've got a product of some things, and so now here it's kind of nice to think if I take the derivative of one of them, maybe I get the other. So derivative of sine is cosine, so I'm going to let u equal, this one's maybe a little trickier, but I'm going to let u equal the sine, and remember, sine squared 3x really means sine of 3x quantity squared. So I'm going to start with, and the other term also contains 3x, so I don't think we need to worry about that so much, because when we do the derivative of sine of 3x, we're going to end up getting a cosine of 3x. So if I let u equal sine of 3x, right, that would mean that du is going to equal cosine 3x times 3, right? Cosine 3x, and then there's a chain rule there, would be times 3 again. So it'd be like 3 cosine 3x, I'll just go like this, times 3. Now, that 3, again, I'm going to divide that, so that I have a 1/3 du equals cosine 3x. Okay, now I think I can make all my substitutions here. I should be able to make this fit pretty well. So where I had sine of 3x quantity squared, that's going to be u squared first, right? So it'll be u squared. And then this part of it, cosine, oh, I forgot to say dx. I'm sorry, at the end of this, because it was, du dx, and I didn't put that at the end. So I do have cosine 3x dx, so there's cosine 3x dx, and that's going to be replaced with 1/3 du. So the 1/3 out here, and the du right there. Okay, and now when I integrate this, that's u cubed over 3, so I get 1/3 times u cubed over 3 plus c, which is now going to be u cubed over 9 plus c. and the u, sine of 3x. So when I substitute that back in, I get sine 3x to the third power. You know, I could put it here. Sometimes that gets a little confusing. I'm just gonna be safe and say it's to the third power like that, over 9 plus c. Okay, and that is it for the first 4 examples. So we'll finish up the rest of it on the next video.